Good evening. We'll start in 2 minutes. Just waiting for people to join. In case you have any issues in seeing my screen or hearing me, please let me know. Okay, let's get started. Good evening. Welcome to the week 4 live session for the GPU Architectures and Programming course. So, we'll get started with some of the questions that were asked in the previous session. At any point, if you're not able to hear me or see my screen clearly, please let me know. I'll switch internet connections. As of now, I think things are fine, so I'll continue. Okay, So one of the questions I got last week was, when do we use MPI or OpenMP versus CUDA, right? So all of these are, one second. Yeah, all of these are parallel programming paradigms, but they're typically used in different contexts. Now, OpenMP and MPI were primarily, when they came about, they were intended for usage in a CPU cluster, right? But now, of course, all of them support GPUs too. But with CUDA, the difference is that it is limited to GPUs and particularly NVIDIA GPUs. I think we discussed in a previous session that AMD has a certain different um, programming language and a software stack for their GPUs. Similarly, other vendors would also have other things, and there is OpenCL, which is vendor agnostic in a sense. So CUDA is particularly limited to NVIDIA GPUs and it cannot work with CPUs, right? Whereas OpenMP and MPI work with CPUs and GPUs too. And they may have support for other types of accelerators also. And coming to the difference between OpenMP and MPI, OpenMP is typically used in a single machine setting where there are multiple cores, or in a multi-processor setting. Now this is typically referred to as a shared memory setting. You can again look up this shared memory and message passing, right? It's a basic notion in any introductory distributed systems course. You will see this even in parallel programming courses. You will see this reference to shared memory versus message passing. So if you've never heard of that, that would be a basic thing to look at. Again, not very important from the perspective of this course, but more from a general computing perspective. So MPI is typically preferred in not a single machine, but in a distributed or a message passing setting, right? And OpenMP is supposed to be better than MPI when it comes to a single machine. So this is kind of the broad difference between the three and what context they are used in. But of course, the similarity is that all of them are used in a parallel programming context. Hope that helps. Let's look at the next question we had. What is OpenACC? Is it different from OpenCL? I don't particularly remember. So let me look that up and get back to you in the next class. But we also have dedicated sessions for, I think, in the later sessions, week 11 or 12, I think a little bit of OpenCL is also covered. And maybe there is some coverage on OpenCL. Let me quickly look at that. If so, we'll kind of also go into this in a little bit more detail in the later weeks. Yeah, we do have, I think, a good amount of stuff about OpenCL in week 9 and 10. So I'll give you a brief answer on OpenACC in the next week, and then I will get into details if it is relevant from the perspective of your course in week 9 and 10. But yeah, I'll note down your question. Okay, before we move to the next one, the other question I got was, what is the relation between high performance computing and GPUs? Do both refer to the same thing? So HPC is used in two contexts, right? One while referring to a particular application or a workload, and the second is the compute infrastructure itself. So you'll hear people talking about HPC saying, this cluster of very powerful computers, or all these supercomputers put together, right? That is referring to the compute infrastructure of HPC. You'll also hear about saying, climate modeling HPC application. So that is from the workload or application perspective. Both of these are valid ways to kind of look at HPC. I just wanted to point out the difference. But broadly, HPC refers to processing complex calculations at very high speeds using powerful supercomputers or clusters. So typically this is all done in parallel across these multiple supercomputers or clusters. And typical example would be something like a climate modeling or some very, very um, intensive simulation, right? These are all again very parallel applications typically. Now, when HPC started out, it used CPUs and supercomputers a lot more than GPUs. But of course, once, and you'll see why this is, right? Again, there is a lot of inherent parallelism in these applications, and obviously GPUs can exploit that parallelism in the application to give you more performance. So GPUs are now finding increasing use in HPC too. But the moment you say HPC, it does not imply that there are GPUs being used, right? It may or may not have GPUs being used. The other way, if you look at HPC as this is when you look at it in terms of a compute platform, right? Do HPC compute infrastructures always involve GPUs? Not really. HPC workloads, again, if you look at it from a workload perspective, GPUs are used in HPC workloads. They're also used in AI and a whole variety of different workloads. Basically, whatever workloads have, apart from the original graphics workloads that they were intended for, whatever workloads exhibit a high degree of parallelism, GPUs are well suited to those. So those are the two perspectives of looking at HPC and GPUs. Hope this gives you some idea. I've also put in a link to what is HPC to people who have never heard of it. Feel free to go look at this afterwards. Okay, we'll move to the next question. Are branch predictors used in the latest GPUs? No, first of all, branch predictors are completely not there in GPUs. And again, why is this? Like I said, I think I briefly mentioned this last week. That is due to the architectural design of GPUs. You know, this whole concept that you've been hearing now, that these threads execute in lockstep, right? So at this point, I kind of decided that we'll revisit this question because I think you do have a branching kind of examples. Yeah, I think warp, divergence and some of that in probably week 5 will cover this. So you'll be better able to appreciate why there is no necessity for a branch predictor or why branches are not suited for GPUs in week 5. So broadly the answer is no, again due to architectural reasons. But we will revisit this in detail once all of you have had a chance to go through warp, divergence and scheduling. Okay, yeah, this was something that was pending for a while. So just some caching terminology. So whenever you're trying to access data, so remember, keep your memory hierarchy in mind again. So you have the processor, you have main memory, and you have the cache sitting in between, right? For a little bit of context. Again, you might have different levels of caching. If you notice in modern CPU processors, so again, this caching that we spoke about in week 0 and week 1, we were talking about CPU caches, just to be clear. But this terminology broadly will apply even to GPUs, right? But let's go back to the CPU analogy. So all of you might have heard of L1, L2, L3, and then your main memory, right? So there are multiple levels of caching. But basically the whole idea of a cache is something that sits between your main memory and the processor, and it is smaller but faster. So if main memory is of course much larger, but it's slower. So if you find something in the cache, it's basically beneficial because you're able to access it faster and you don't have to go to main memory. But again, cache is small, so the way you design your caching strategies and your eviction algorithms will decide how often you need to take a penalty or you need to take a hit. You need to kind of suffer that performance degradation and go to main memory. So the terminology is very simple. If the data is found in cache, it is a hit. It's called a hit. And this means that your data can be accessed quickly. If it's not found in the cache, it's referred to as a miss, and the associated delay, basically that you have to go to main memory, is referred to as a miss penalty. And you'll often see problems giving you a hit rate or a miss rate. Typically this will be fraction of the time the data is found or not found, and the hit and the miss rate will sum up to 1 because you either find it or you don't find it. So this is a broad recap of the terminology, and I wanted to quickly go through this question. I think we kind of visited it in week 1, but I said I'll get back to it and confirm the answer. So I checked on this. So let's go through it once. A CPI of 10 was observed from simulation experiments conducted with a perfect cache with for a processor with clock rate 5 gigahertz. 64 KB L1 cache having a miss rate of 4% and a penalty of 60 nanoseconds is proposed to be used. What would be the CPI with the 64 KB L1 cache? So this, I think the confusion was that some of you were asking me if this observed CPI needs to be multiplied by 0.96. So no, not really. I checked on this, and this is kind of the time it takes even when there is a cache hit, right? It's basically like a constant time. So I know some of you might have, this kind of calculation. When you do an cache access time calculation, you're typically used to doing hit rate into that access time plus a miss rate into that miss penalty time, right? So this question probably looked very similar, but here this ideal CPI of 10 is something that you would is something that's a constant, right? And in addition to that, you would have, whenever there is a cache miss, you would incur extra cycles. So that is what we are trying to calculate here. So the observed CPI would be 10, and then the penalty for the cache miss, which happens 4% of the time, is 60 nanoseconds, which translates to 300 cycles based on the clock period, right? So the penalty would translate to this many, this 0.04 into 300 plus 10, which comes out to be 22. I've also linked, I think, a course lecture on cache performance, which goes into some details of this. For instance, what is the ideal CPI? How do you calculate the CPI when given the ideal CPI plus this thing? So for people who still find this a bit confusing, please go through this. There are a number of solved problems here as well, I think. So go through it and let me know if you still don't understand something. Okay, let's see what was next. Yeah, this was also something from the earlier weeks. So someone had a question as to, so if, again, a quick recap for people who don't remember. So the cache structure, right? You had all of these fields saying the line or the block, the index and the tag, right? So someone said, why does index have to be in the middle? Can it, for instance, be here, right? That was a question. So if you, interestingly, this was something I wasn't really aware of before someone asked me this question, but when I looked it up, there is a reason for this, right? So from a set associative perspective, if you look at this, basically you can think of a set as a restriction on where data from the main memory can be put into the cache. Remember in the previous week, we went through that bookshelf analogy, right? Given a book, you know which shelf it should go to, that sort of thing, right? Now, if you have this set bit as the highest order bit, then large consecutive ranges in main memory would map to the same cache set, which causes many conflicts and evictions, ultimately resulting in poor cache performance due to all of these misses, right? So that's one of the reason it's not the higher order bit, and it's kept in the middle, and tag is kept as the. So this has to do with things like data locality. When you access elements that are for instance, consecutive elements of the array, you want to get a good hit rate, you want your cache to give you a good hit rate, and you basically want to exploit that notion of data locality. But if you make these the highest order bits, then that would not happen. So this again might be a little subtle, might be a little difficult for you to understand. Again, I've left links to a couple of things, because again, these are not very central to the course. These are from week 0 and week 1, which kind of go to your prerequisites on computer architecture. So it's not very relevant from the GPU side of things, but it's just something interesting to know. So I've left links to again a course lecture slide which talks about this, and a Stack Overflow answer which I think gives you an example. So whoever asked this question, if you're still curious, please look through the details and see if it makes sense. And again, whether this holds in all the cases also, right? So this was answered from a set associative perspective. If it's fully associative, it won't matter. You can think about what happens when it's direct mapped. So these are all nuances, but again, a lot of this design need not be just a matter of convention, right? It need not be that you exchange the positions of two fields and things are the same. They're all very well thought out and designed, something that we may not be aware of when we read textbooks, but asking questions is always nice. So when you're curious about something, if you feel why should this not be in the middle, again, that's a good question to ask, and all of us learn something from it. So feel free to ask those questions in these lectures, and I'll try my best to kind of come back to you with the answer. Okay, so I think with this we have covered all the doubts that were asked previously, right from week 1 to week 4. So we are at 1/3 of the course. So again, I'll pause here for 2-3 minutes, and if you guys have any questions from any week so far, week 1 to week 4, please ask them on chat. I'll again make a note of them and come back to them in the next week. But please take this opportunity to ask them. After this, we'll go into the recap of week 4. Is the course going well for everyone? Are things okay now? I think 4 weeks is a good time to see how you feel about it. And yeah, someone else asked me about collab, I think. Whoever asked, were you able to get it working? I think someone else pointed out that there was a tutorial video, which I also noticed and then watched. So that actually gives you detailed instructions on how do you do it on cloud and how do you do it on bare metal on your own system. So could have worked. Great. Good to hear that. So for anyone else who's having trouble and who hasn't noticed that there are tutorial videos, I'll mention it again. Week 3 has a couple of tutorial videos mentioning how you can set up CUDA either locally or use Colab, right? So these are detailed instruction videos. So please watch them, because it's good to try out these examples that are discussed in class on your own also. That will give you a good hands-on experience of GPU programming. Any other questions? I'll wait for a few more seconds. Also, I think I didn't pick up any questions from the discussion forum this week, but I noticed a couple of you had doubts on the assignment questions. So again, I will not get into those, because the TAs who set the assignment questions and who have the answer keys are different. So they answer your questions on assignment specifically. So I think one question somebody had asked that the question and the options didn't match, and they had clarified that that is correct. So for people who are not aware of this, please again check the discussion forum regularly. And other than that, I didn't see any questions in week 4 content, so I don't have anything else that I'd like to highlight. But if you guys have any doubts, waiting for one more confirmation. Yeah, I think I see that you had asked something about problem 5 or something which you didn't get an answer to. Yeah, but typically if the question is incorrect, the marking will keep take that into account. But again, I can't comment on this because I don't set the questions or get involved in the grading. So the official TAs will have to reply. Any other doubts that are asked there apart from the assignment questions, I will also discuss them here to make sure you understand well. And yeah, I see a similar question on, I think, week 3. Again, I don't know if the solutions for that have been released. Okay, solutions have been released. This maybe we can go through this. I'm just seeing it for the first time today, so I didn't pick it up. But we can discuss. One more question on week 4, 7th question. Okay, I think week 4, the deadline is not yet over. So I think it would be better if you ask on the discussion forum. Yeah, I think it's 21st, so you can ask it there. Because the TAs who have set this assignment and who grade it kind of are there, and they will reply to you. Once the solutions have been released, if you don't understand a particular solution, we can go through it here. That is fine. But before the deadline for submission of an assignment, I am not allowed to discuss a question because you guys are supposed to solve it on your own without help from these sessions directly. But if you think that some data is missing or the question is incorrect and things like that, please post it on that forum so that you get clarity as soon as possible. And if you don't get a reply, sometimes there are a lot of emails and the TAs might miss out. Give it 2 or 3 days and please ask, like put in a reminder note saying that this is due on so and so date. Could you please clarify my doubt? So they'll maybe look at it and let you know. Yeah, any other questions or doubts before we move to the recap part? Okay, if not, then let's move to the recap. So in week 4, we broadly looked at multidimensional data and synchronization. So we looked at, so earlier itself we had seen this notion of launch parameters, your grid and block dimension. So now we are particularly looking at multidimensional grids and blocks and the mapping between kernels and data. So a lot of questions you'll notice in week 3 and 4 that kind of test your understanding of this mapping between data and kernels. So they'll ask you a lot of things like, for this particular problem size, how many threads do you need or how many blocks do you need? So looking at the code, again, last week we discussed some of these and this week also we'll refocus on them. But what you need to keep in mind is how much work is a particular thread doing and how many elements of the data is a thread handling, things like that, right? This mapping between kernels and data you'll see again in a lot of questions. And then we also looked briefly at synchronization. Let's go through some of those concepts and then jump into the problem solving. So again, as a quick recap, a grid is a 3D array of blocks and a block is a 3D array of threads. And both of these are specified by a C struct type called dim3. And any unused dimensions are set to 1. So instead of a 3D, if you're using 2D, it will be x comma y comma 1. right? And if you're using 1D, it will be x11. I think this is something you saw in the last week as well. Now, grid dimension dot x or y or z can range from 1 to 2 to the power of 16. So again, remember that some of these limits are defined by the GPU architecture itself. For instance, remember that there is a limitation on number of threads per block, right? Which says that I think it is 1024. So wherever you see such limits, remember that they are kind of a feature of the GPU architecture, so they can change. So anything that you see in your course may or may not be reflective of current architecture. So make sure to look at it from the current architecture perspective. Coming particularly to the 1024 that I was talking about, I think still even for the latest GPUs it is 1024, but it's always good to check that, not from the perspective of your assignments, because in your assignments every question will explicitly state those assumptions. In case they don't state them, you will have to use the defaults that are taught to you in the course. But from a real world perspective, you will need to know how some of these assumptions change with the latest GPU architectures, because you may not be working with a very old GPU, right? You may be working with something that's relatively new, maybe in the last 5 years or so. So remember to look at these things from the perspective of whatever you are using also. And again, every block can have block ID dot x, y and z. All threads in the block sees the same value of block ID x, y and z. Basically, any thread that is in a given block will have the same block ID along all dimensions, which makes sense, right? That's why it is in that particular block. So these three coordinates define one block. So all threads in that block will see the same three coordinates. And again, block ID dot x or y or z should belong to 0, grid dimension dot x, y or z minus 1. So it cannot go above that. Again, because of the way the grid, block and the threads are defined. Okay, so we'll again look at one particular example. So here you have two DIM3s defined, 2, 2, 1 and 4, 2, 2, and the launch configuration is x, y, which is basically 2, 2, 1 and 4, 2, 2. So now coming to, so the higher level is your grid, and remember that it's always z, y and x. And these limits of z, y and x will depend on these values. So now remember that this is unused, right? That's what the 1 indicates. So basically this becomes two-dimensional. Your z is not at all used. So the z will always have the value 0 here. And your x and y will take values as dictated by these two parameters. Now here both of these say 2. So both x and y will range from 0 and 0 to 1. So again you have 0, 0, 0, 1, 1, 0, 1, 1. And this is your grid. Now let's come to the block part of it. The block is three-dimensional. It has all three possible things. Again, notice that it's z, y and x. So it's 4, 2, 2, which means that one of the dimensions will range till 3. Basically your x will range from 0 to 3, y and z will range from 0 to 1. So again, you'll notice here it starts from 0, and the z part of it varies between 0 and 1. Similarly for the y, but if you look at the x, it ranges from 0 to 3. 0, 1, 2, 3. So this is what your block IDs look like. So again, how many threads would you have? Totally, you would need to multiply both of these. And in a given block, how many threads you would have? Again, you can calculate that from these things. So these are some things that you can figure out from the launch configuration that's given to you. Okay, we have one more example. Again, I think we went through this from a 2D example last time. So it's very similar here, but you need to understand this at a conceptual level. So again, this might be a bit complex. So if you want a simpler understanding, I can try and give you a visualization that's maybe a little easier than this to figure out how you get these intuitively. For 2D, I think we worked it out, and that's probably a little easier to understand. Here you have all three dimensions for the block size, so it may be a little more difficult to calculate this. Let's go through this, and if you feel an easier way would help, you can let me know on chat, and I'll check to see if I can find a easier uh, logical explanation of how you come up with this block number, thread number, and global thread ID. So again, in questions we would explicitly provide info that thread block position marked as ZYX. Um, I think most of your questions don't, right? In week 4, if you look at least the questions that I brought in for this week's, this one didn't have it. So there are two ways that questions will go about this, right? One is they don't say anything. If they don't say anything, it means that the defaults that you were taught in class would hold. So whatever conventions, whatever variables, whatever limits were used in the lectures, those would hold. In case it is explicitly stated as something different from what is used in class, that would hold. So if your question does not mention it, then you could just go by what is taught in class. That should be fine. If in case the answers don't match, you can say that I considered whatever was used in class since the question did not explicitly state otherwise. That's a valid argument to make. Okay, so coming back, how do you calculate the block number? Okay, question 5 is wrong. Okay, I'm guessing you're referring to the week 4 questions. Okay, question 5 is wrong as block dimension mentioned as 5.2 and thread location specified as 3.1. Yeah, I looked at your question, but again, I've not seen the assignment in detail. So it may or may not be wrong. If you think based on whatever is taught in class, unless the assignment explicitly states that we are using a convention different from what is taught in class, right? Instead of ZYX something else, you can assume that whatever is taught in class holds and then say that this doesn't make sense. It may be wrong. The TAs will be able to give you more. Yeah, I think it would be better if you ask this there, since there are 3 more days for the assignment submission. Getting an input from the assignment related TAs would be helpful for you in answering that. Yeah, but by default, what I would say is, unless the question explicitly mentions something different from what is taught in class, you follow the notations that are taught in class. That should be fine. Okay, so so first, how do we calculate the block and the thread number? So the block number is calculated as block ID dot z into grid dimension x and y, the product of the two, plus block ID dot y into grid dimension dot x plus block ID dot x. Again, I think this was explained in class. So you're trying to calculate all the uh, you're trying to enumerate all the blocks that came before this particular block based on the x, y, and z, right? So the last part that's given to you is kind of like an offset, but before you add that offset, you need to account for the previous things. So last time there was only one term that was before the offset because it was a 2D. Now you have a 3D. So think of this as kind of a cube, right? And you're given a a cube or a cuboid, and you're given a 3-dimensional coordinate for the block number. You need to enumerate all the things that came in, maybe the certain number of planes that you have to traverse, right? And then maybe the rows that you have to cover, and then finally the offset, which would give you that particular block. So this is an intuitive way of thinking about it, and if you actually try it out, you'll understand it better. So that is to get to the block number. Similarly, for the thread number, again you have a very similar formula, except that whatever was previously grid will now go to the lower level in the hierarchy, which is the block. So now you take the z part of it, multiply it with block dimension dot x and y, and you take the y and multiply it with block dimension dot x, and then finally add up the thread id dot x. That would give you the thread number. So this is how you get the block number and the thread number given the three coordinates, right? Then you are trying to calculate the global thread ID. So given the grid, you'll basically be given these two pairs of three values. You need to, if you have to find the global thread ID, first you will figure out which block it is from, and then the thread number within that block. Now you are trying to find across all blocks what is the global thread ID. So you take the block number that you have calculated and account for all the previous sort of blocks that are there, which you get by multiplying the x, y and the z. So there are that many blocks before this, and then you just have to add an offset. So because you have calculated both of these already, this becomes very simple. There's just total number of threads in this many blocks, and then the thread number. So that would give you, so this block dimension dot x, y and z basically accounts for all the previous threads, and then you have an offset, which is your thread number. So this would give you the global thread ID. I think an example also was worked out in class for this, so I've not gone into details here. But if someone finds this confusing and would like a more detailed explanation on this, please let me know on chat. I'll pause here for a few seconds and then move to the synchronization part of the recap. Okay, if this is clear, let's move to the next part. So the next part is synchronization, right? So before we get into synchronization, we have to revisit what guarantees the GPU gives you, right? Because there is this notion of blocks and threads, and as programmers, you write code for a kernel. You might have seen in some of your example programs that were discussed in class, as well as the fragments that you are given in assignments. You write code for a kernel, typically defining that this kernel operates over some elements of data. It might be even one element in your array, right? Now, given this, what guarantees does it give you, right? You're going to launch this kernel using the launch parameters that we just discussed, right? The number of blocks, the number of threads. But what guarantees do you get? or what can you not expect, because you need to know this as a programmer to write code that actually works properly the way it's meant to. So these are the two things that you need to remember. So every block can execute in any order relative to other blocks, right? This is something you have to always keep in mind. And why is this designed this way? It's because if I put synchronization constraints or some constraints on the order of execution of blocks, then I can't fully parallelize this computation in a sense, right? So depending on the hardware, I'm not saying that the order of execution, I'm not saying that they won't, they will always run in parallel, right? You may not have enough resources or enough SMs on the GPU for them to run in parallel, and they may run, for instance, if you have 8 blocks, you may run 4 blocks first and then 4 blocks or something like that. That's quite possible. But as a programmer, you can never assume anything like that, because that part is completely not exposed to the programmer. So as a programmer, what you always assume is there is no ordering guarantee given by CUDA to you. Every block can execute in any order relative to other blocks, and this is what kind of enables scalability. But given this, how do you enforce some kind of synchronization? So you can only enforce synchronization constraints to threads inside a thread block, and these threads may cooperate with each other and share data, and you can use this construct called sync threads for enforcing synchronization. So let's look at this same example, right? So here we had this triangle sum computation where every thread kind of computes the sum up to certain elements, and the last one computes the sum of all these elements. Now you, and once every thread finishes computing these elements, then the total sum is computed by the last thread. That's what you want, right? So here you need to have a sync threads put in place before you do this part. So this j equal to n minus 1, and you sum up all these elements and put it to the last element. This needs to happen explicitly after a synchronization call, because otherwise you don't know if these elements have the right values. They may or they may not. As was discussed in class, you don't have any guarantees on that. So you'll have to use the sync threads primitive to enforce this synchronization here. And again, this is possible because you're asking for a synchronization among the threads and not some kind of ordering between blocks. So that's the summary of synchronization. So with this, we'll move to the problem solving. Let me quickly take a look at how many problems we have. So before we move to that, any other doubts or questions in week 4 content particularly? Anything that you would like explained in more detail, anything that's not clear or that's a bit confusing? Please take a minute to think about it and let me know. Since we finished all questions from previous weeks, I have a little more time in the next week to answer your questions, or even to go into detail into a particular concept that was discussed in the videos. So feel free to utilize that opportunity, right? If not, we'll just end the session early. So since we have 2 hours, I'm very happy to teach 2 hours, but the 10 questions typically takes around an hour, and your recap takes half an hour. So I have half an hour left, and I think I got 2 questions today, 2 or 1, that was about it. So if there are any other doubts, please ask them, and we can, it can even be, for instance, that I didn't understand this 3-dimensional calculation of block number or thread number. We can go into that in detail in the next week. So anything like that, feel free to ask. If everything is clear, I'm very happy, and that's perfectly fine too. But in case you have doubts, don't hesitate to ask. I'll wait for a few seconds, and then we'll start off with the problem solving and then take a break. Okay, if there are no questions, let's get started with the problems. Compute kernel 1, which takes input 1 and input 2 and gets you an output, takes as arguments two 1D arrays named input 1 and input 2 of total size data size, processes them and writes to an array named output after performing the following operation. Output I equal to input 1 of I star input 2 of I star 4. Launch config, three-dimensional grid of dimensions 4, 2, 2 with two-dimensional blocks of 32, 32, 1. What is the value of data size? Basically the size of these 1D arrays given the launch configurations. I'll give you 2 or 3 minutes to solve this and then we can discuss. Okay, D, we have one answer. Anyone else? D, okay. D question mark, okay. So again, I would say pay attention to how many elements the kernel is taking care of, and therefore how many such elements are there based on your grid and your block dimensions. D, okay. Anyone else who's still calculating? Okay, let's discuss the answer. So it is D, all of you got it right. So here it's very simply the size of the array is the number of threads. So how do you get the total number of threads? You multiply all of these together, right? Because multiplying this will give you number of threads per block and multiplying this will give you number of blocks. So number of blocks into number of threads per block will give you the total number of threads. So 4 into 2 into 2 into 32 into 32 into 1, which gives you 16,384. That's your total number of threads. Now notice the subtlety here that each thread works on one element of data. Therefore, your number of data elements or the data size is same as the number of threads. This may not be the case in every question. So don't by default when you are asked about the data size, many people will look at these two, multiply them together and mark the answer. That is correct in this case. But notice the inherent assumption here that the size of the array is the number of threads. Always make sure to verify that. You may be given a kernel where each thread is handling two elements, right? So you have to be careful in answering that. But hope this is clear. I'll just wait for a few more seconds. If you have any doubts, you can ask me. Okay, I'm guessing it's clear. Let's do one more question and take a break. Okay. Compute kernel 2. This takes as argument a 1D array named input of total size data size, processes and writes to array named output. The input array to this function will be the output array obtained as a result of process kernel 1. I think that should be compute kernel 1, but yeah. The following operation needs to be performed here. Output I equal to input I star input I using a two-dimensional grid of dimensions 2, a, 1 with three-dimensional blocks 8, 8, b. What are the possible values of a and b? Again, take 2 or 3 minutes to solve this and then we look at it. We have one answer A. Okay. A, B, okay. B, okay. We'll wait a few more seconds and then discuss. Anyone else? One more answer saying B, okay. Okay, I get why this could be confusing. So let's discuss it and see if it's clearer. Okay, so the answer given to you is A. Now let's go back and try to figure out why it's A and not B, as some of you said. So first of all, the input to this is the output of the previous question, which had the size 16384. So by the same logic that we used to solve the previous question, you know that the product of these 6 elements here should be match up to this number. So let's take the known things that we have here, 8, 8 and 2, right? Which gives you 128 and then your A and B. So if you do this, I think you will get AB is equal to 128. Let me just check that. Yeah. So now you'll see that two answers match this, right? 8 into 16 and 2 into 64. But you have to pick one of these. So you have to, so the answer is decided by this factor. The maximum number of threads that you can have per thread block is currently limited to 1024 across all GPU generations. So if your B is 64, then 64 into 64 crosses that limit, right? But if your B is 16, then it remains within that limit. Basically, that is your deciding factor, which makes A your correct answer and not B. And again, remember that this is something that has nothing to do with this question, right? It's a GPU architectural constraint. So you'll have to keep this in mind while solving all problems, that whatever this block configuration has should always obey this, right? So if you have multiple correct answers, remember to check against this constraint too. So now is this clear why this is the answer? Great. I think we can take a break now. So it's 7:03. We'll come back in 5 minutes, 7:08. I'll leave the call running. Okay, let's continue. So we'll move to, yeah. So a quick recap from this question. Hope it was clear to all of you. But the block dimension is limited by this constraint of total number of threads possible in a block, which is 1024. So here are a few examples. 512 into 1 into 1, less than that. 8 into 16 into 4, again less than that. 32 into 16 into 2 again works, but all 32s doesn't work. So this is something you have to keep in mind for all questions. With that, let's move to the next question. Compute kernel 3. This takes as an input 1D array named input of total size data size, processes and writes to an array named output. Your input array will be the output array obtained as a result of process underscore kernel 2. Again, you can assume compute underscore kernel 2. Following operation needs to be performed here. Output I equal to input of I star I using a one-dimensional grid of dimensions A11 with two-dimensional blocks of 128B1. What are possible values of A and B? So you're given 4 things. Take your time and let me know what's the answer. Okay, we have 2 answers saying A. Anyone else? A, okay. We'll wait for a few more seconds in case any of you are still calculating. Okay, if not, the answer is A. I think all of you got it right. So why is it A? So again, now here you are given 128 comma B comma 1. Going back to the same constraint that 128 into B should be less than or equal to 1024. If you do 1024 by 128, you will notice that 8 is the maximum value that B can have. So this gives you a quick way to eliminate both of these. So you don't need to check this at all. And you are left with only A. Another sanity check I would recommend is to also multiply both of these. So 128 into B into A, which is basically 128 into 8 into 16, which again should come back to your 16384, because if you notice, the previous question just took input of I, multiplied it by I, so the output dimensions don't change. So it could still end up being none of the above, right? In case the A did not match. So pay attention to these things, because again, the concepts that these questions are based on will remain the same. What will happen in your exams and your assignments is that there will be slight changes made to the questions. But as long as your fundamental concepts are correct, you should be able to solve them. So always pay attention to all the possible assumptions that you are making and what could cause a particular answer to be wrong, right? So in this case, even though verifying this gives you the right answer, make sure to verify that the product of all 6 elements also matches what you have. Of course it does, that's why A is the right answer, but always do those checks. Hope this is clear. We'll move to the next question. So this week, I think most questions will be very similar to this. So once you get the hang of answering them, all of them will be very easy. Okay, we'll move on. Consider a kernel launched with the following launch configuration parameters: 221, 32, 32, 4. What is the total number of CUDA threads that are spawned for the given launch configuration? This should be very easy, but I'll give you a minute. Okay, we have one answer, A. A, A, okay. A, okay. Anyone else? Okay, I think this is fairly simple. So let's look at the answer. It is A. Okay, we have one comment saying max threads allowed crossed 1024. So let's go back to that, right? Let's clarify this because this is very important for you to understand. So this limitation of 1024 is the total number of threads possible per block, not the total number of threads across all blocks. So here what we are doing is, if you multiply this much, right, 32 into 32 into 4, you will notice that it is still within 1024, right? Okay, I see what you mean. You're talking about the 32, 32, 4. Okay, fair enough. That should not theoretically cross 1024, but you're not asked if this is a correct kernel. If you were asked if this is a valid kernel, then you can go ahead and say no, because this is crossing 1024 and that's not possible. But here you're just asked about, if this kernel were to be launched, what would be the total number of threads launched? So the answer is A. But it's good that you noticed that, right? That's a fair argument. So in case you are asked in a question whether this is a valid kernel, you could very well say no, and that would be a correct answer. Any other doubts on this? Okay, if not, let's move to the next question. For the launch parameter configuration provided in question 4, what are the min and max values of thread ID x dot x? You are given 4 options. I can scroll back to the previous question if you want to look at it. So it's 32, 32, 4, and you're asked about the min and the max in the 5th question. Any answers? C, 0 to 31. Okay. C, okay. C, C, C. Okay, I think all of you are reasonably confident about C. Any other answers? C. Okay. Let's look at the answer. It is C, 0 to 31. So again, block dimension dot x equal to 32 for this launch configuration. So threads in the x dimension would have IDs ranging from 0 to 31. So your option C is correct. I think this is straightforward. So we'll move to the next question. For the launch parameter configuration, what is the maximum and minimum values of block ID x dot y? Again, very similar question. A, okay. Anyone else? A, okay. C, again you're asked about block ID here, not about thread ID. A, okay. Anyone else? Okay, let's look at the answer. Yeah, A is correct. Again, grid dimension dot y equal to 2. Therefore, in this launch configuration, so the thread blocks in the y dimension have IDs of 0 and 1. That's all. So min and max is 0 and 1, which is your option A. Okay, next question. Consider a 1D CUDA kernel that computes on a 1D array A of size 2048 with launch parameters 32, 64. Each CUDA thread operates only on one data point. On what data point will the thread with thread id.x equal to 20, block idx.x equal to 20 operate on? Assume that thread IDs along the x dimension represent rows and thread IDs along the y dimension represent columns. Again, this may take 2 or 3 minutes. Take your time to calculate. So this again goes back to that mapping of threads to elements, right? You're being asked which data point will a particular thread operate on. Think about it. We have one answer C. Okay. Any other answers? Think about it. If you're given, let's say, block id x dot x equal, this is 1D, right? So it's very simple. So if you're given, let's say, start out with block id x dot x equal to 0 and just a thread id x dot x, what would it operate on? Which element would it operate on? Then maybe go with block id 1 and think about what element it would operate on. I'll give you one more minute. If you're unable to, then we'll just discuss it. Anyone? Okay, if not, we'll just look at the solution and then maybe you'll understand. So C was right for whoever got it correct. So again, for any point A of x, block id x dot x into block dimension dot x plus thread id x dot x would be how you calculate the thread id, right? So this is that mapping of thread to element that you write in every kernel. Remember, I think we had it in some of the examples. So here it's implicit. For instance, it works on the same element. But remember, in last week's examples, you had that. You had basically one line calculating which element a particular kernel or a thread would process. Yeah, this is very similar to, this is basically the global number itself in this case, because again you have a 1D array. So whatever you get as the global thread ID, then you would simply say that this would map to that particular element because you have a 1D array. So basically you can think of it as, like I was saying, if you have the block ID as 0 and the thread ID as a particular value, let's say 10, then thread IDX, that particular thread would be working on the 10th element. Now if I say block 1 thread 10, you have to keep in mind that the block 0 will be working on a certain number of elements, right? which is defined from this launch parameter. So you first account for that by using this part, your block id x.x into block dimension.x. And after that, in this case, you're given that the block id is 20 and you know that the dimension is 64. So this many elements would have already been as allocated to the 20 blocks that came before this. And then in this particular block, the thread id, the thread with id 20, you'll have to account for the previous threads, right? So that's again adding a 20, which comes to 1300. So essentially this is same as your calculation of global thread id. If you have a 2D matrix, it will be slightly different from this, which I think we have a question somewhere below, so we'll come back to that. Is this clear for now? I'll pause here for a bit and we'll move to the next question. Okay, I'm guessing it's clear. Yeah, there comes the 2D matrix and 2D kernel. So consider a 2D CUDA kernel that computes on a 2D matrix of size 2048 cross 2048 with launch parameters 32, 32, 64, 64. Each CUDA thread operates on only one data point, on which will the thread with thread id x equal to 0, y equal to 0, block id 10, block id y 10 operate on. Assume that thread IDs along x dimension represents rows and thread IDs along y dimension represent columns. So you have 2D data and 2D kernel here. So think about how you would extend the calculations in the previous question. Okay, we have one answer, C. Okay. Anyone else? A, D. Okay. This seems to be very confusing. Okay. I'll give you a minute more. Okay, how to read the launch parameters? Is it grid x comma grid y, block x comma block y? Yeah, in I think what was discussed in the lectures, was it y comma x or x comma y? In this case, it wouldn't make a difference because both are the same. But whatever was used in your lecture, follow that typically for questions. Because these again x comma y. Okay, then follow x comma y. I'll have to look at it once to confirm. I can check that also and get back to you. But whatever, if you're asking specifically for the week 4 assignment which you need to submit, then yeah. Oh, how to read as in grid comma block ID. Yes, yes. First is grid and then the block. That's correct. Any answers? C. Okay. C. Okay. Okay, let's look at the answer. It is C, M640, 640. Why is that? So if you go by the calculation side of things, right, you would come up with this sort of a mapping. I think we did this in last week where we had 2D kernels and 2D data. So you take your block id x.x, multiply it with block dimension dot x plus thread id dot x. This is kind of the same offset plus previous things you've dealt with, and similarly a y, right? Exact same thing except that everything is y. Then now you take this launch configuration that you have and you substitute it, and remember that your thread idx both are 0, so you just need to calculate this part and this part. Again, both of those are 10, both of those are 64, so both your x and y come out to be 640, 640. For those of you who find these formulae very complicated to remember, or it's very difficult to get this sort of question right, think about it on a logical perspective. You're told that this thread idx in both dimensions is 0, right? So this means that there is no offset in a sense. You're being asked about the first thread in with this block id, and you're also told that every thread operates only on one data point. So you'll simply need to compute all the blocks that came before, which in this case is 10 blocks. You're being asked about the very first element after that. So again, remember that each of these would process this many elements, right? Because why is that? Again, because you have this many threads per block, 64 into 64. So now you have 10 such blocks, meaning that when you get to the end of this previous 10 blocks, you would have processed 640, 640 in both dimensions. So you're being asked about that very first element. So this would be your answer. So this is again going at it from a very logical perspective. You can always try to reason about it, saying that if everything was 0, which element would it process? Then add in one dimension, see if you can logically figure out. And then if you were given a particular thread ID along with the block ID, can you figure out? It will basically lead you to derive this formula in some sense. So I noticed that this question 7 and 8, some of you had difficulties, right? So revisit that part that we discussed about the 2D mapping of data and this thing. But rather than trying to remember these, see if you can get a logical understanding. We went through this last week, so I'm not going too much into detail. But if you find it particularly difficult, then let me know and we can again go through it. But this will be important because you could have 3D kernels, you could have 2D data, things like that. So for people who find it difficult to remember these, you might get very confused because the actual formulae themselves will change. So what I would suggest is being able to come up with these on the fly based on first principles, based on logic. But hope this question is clear. We'll move to the next one. Okay. Consider a kernel processing a 2D matrix of dimensions 1024 into 1024. Each thread is assigned to perform an operation on a single element of the matrix. The kernel is launched with the following grid and block configurations: A32 2, 32B2. For a hypothetical GPU architecture where the maximum number of threads in a block is 512, what are the values of A and B? You can take a couple of minutes. This is very similar to the previous questions we solved, except that the constraint now changes, which is explicitly stated in the question. Okay, we have one answer saying C. Okay, we have one more answer saying A. Again, I think we discussed a very similar question before, right? Where two answers were possible. So in that case, remember what is the secondary constraint we use to figure out the right answer. Make sure that all constraints are met. Okay, we have one more answer saying A. Okay. We'll give you another minute. D, none of the above. Okay. D, none of these. Okay, I think we can discuss the answer. Okay, we have someone else saying C. Okay. Any other answers before we discuss? Okay, let's take a look. It is C. So first, let's start with this constraint of 512, right? So it says number of threads per block should be less than equal to 512. So 32 into B into 2 is 512. Then you will see that 8 is the maximum value that you can have to satisfy this 512 constraint, which rules out B, and A and C are possible contenders. Now, remember that the other constraint that we had to evaluate was that here we are told that the dimensions of the matrix are 1024 into 1024, and every thread works on a single element, which means that the total number of threads you get by multiplying all 6 of these should be equal to this into this, because every thread works on one single element. So 1024 into 1024 is on the right, and you have 32 into 2, and if you take option C, you get 32 into 32 into 2 and 32 into 8 into 2, which is 512. So this becomes 1024 and this part becomes 1024, which matches this, which I think is not the case in A, which is why it is eliminated, because this is 16 into 8, which would be, I think, lesser than this, right, by definition. So C becomes your correct answer. So we evaluate for two constraints here. One is the one explicitly mentioned as the maximum number of threads per block is 512. The other is the one that implicitly comes by saying that every thread works on a single element of the matrix and the matrix is of size this. So looking at both of those, C is our right answer. Is this clear now? Okay, great. Let's now look at the last question for today. Consider a kernel processing a 1D array of 4096 elements where each thread is assigned to perform an operation on a single element of the array. The kernel is launched with the following configuration: 16A2B24. Assuming a hypothetical GPU where the maximum number of threads in a block is 256, what are possible values of A and B? You have four options. You can take 2 minutes. Any answers? Again, very similar to the previous questions. B, okay. D, okay. Yeah, there is an all of the above in this question. So, yeah, make sure to evaluate all of the options. B, okay. Anyone else? If not, let's discuss the answer. One more saying B, okay. Okay, let's take a look. So it's D, all of the above. So two constraints again. The maximum number of threads per block is 256 and your number of elements is 4096, and every thread works on a single element, right? So for the 250, so if you first use this 4096 constraint, you get 16 into 2 32 into 8 into AB equal to 4096. I think that evaluates to a product of AB equal to 16. So all three options are correct: 4 into 4, 1 into 16, 8 into 2, right? The next constraint is 256. So 2 into 4 is 8, and 8b should be less than 256. Again, 2 would work, 4 would also work, and I think 16 also works. So again, all of these are valid even given both of those constraints. Therefore, all of the above is the correct answer. Is this clear now? Okay, great. Okay, I think we are at the end of our questions. We have 10 minutes to go, so I'll hang around for a couple more minutes in case any of you have doubts. Please put that on chat. If not, if you have no doubts, then we are at the end of today's session. Thank you so much for joining and hope this was useful and look forward to seeing you next week, and thanks for keeping it interactive. Thank you. Thank you. Thanks. If you have no other questions, feel free to drop off. Sixth question from week 1. Okay, so is this the assignment question? Glad to hear that. Thank you so much. Okay, I will take a look at that and then maybe discuss it in the next session. Any particular, the recorded session will be uploaded to YouTube. So there is a sheet that I think is shared with you guys. So in that sheet, you will find the link to all of these. So I think there's a tab called problem solving session in your course tab. And then you can just say click here and it will take you to the sheet. I can just quickly share the sheet link here in case you have trouble finding it. You can go look at this. So I upload recordings within a day of the class. So I would do the same thing and then put it by tomorrow. So you can find the link from that. I won't explicitly share it. The sheet will be updated after every class. Okay. So you had asked it on the discussion forum. Okay, great. Then I'll take a look at that. I think I remember this branch prediction question. Okay, I'll take a look at it and maybe get back to you. We can discuss it in the first part of next week's session. Thanks for asking. You're asking about the branch outcome. Okay. Any other questions? Outcome of the branch. So you're asking that the outcome of the branch is not given. I think this is one of those common questions. Yeah, question 6, right? So this is a bit tricky with this particular course. I've seen that 3 or 4 questions share the same data. So you will need to, even though it might kind of, you might miss that. I see that there is a common block for question 5, 6, which actually gives you the outcome of a branch. So along with reading each question, just check that there's no common data that's used. So I think that's why you kind of missed that. So there is the branch outcome given as common data in above question 5, and which is applicable even for question 6. And that's why that part is, I think you didn't find it in the question and you had asked. Does that help? Great. Okay, if there are no other questions, we'll end today's session here. See you again next week. Thank you so much.